हाँ नवकृष्ण स्टार्ट मोर ऑडिबल हो तो हाँ शेयर करी हाँ I'll share once you start then I'll share no over okay acha let me just I because I am not able to see no okay I'm sharing my screen just wait hold the phone okay like I hope all of you are able to visual Asila screen okay is it visible now I'll maximize it let me switch off my camera okay now it is visible अच्छा देखो ऑडियो इज प्रॉपर okay it will okay now it's okay okay ठीक start let me start so sorry for the interruption because I was not knowing that the organizers have already started so first of all I would like to thank the organizers of this Vignan Institute for inviting me for giving a lecture on this topic of deep learning and its application to computer vision. So somebody can confirm, is it the audio is okay? Okay. So the to say about deep learning, as we know that the CNN is the one of the background and base for designing a deep learning model. So I am introducing here CNN, convolutional neural network, followed by recurrent models like your RNN and LSTM models. Then we'll consider on a particular, though there are vast number of applications for computer vision with respect to deep learning, integration of deep learning with computer vision, we can formulate many applications. So here I have concentrated on a particular application. It's very crucial nowadays, and also many research challenges are there. Research is also going in multiple ways for video anomaly detection. So to start with, because we know that deep learning is a subset of machine learning. So as we know that machine learning is main, we consider computer as a machine which takes some data and we try to create a model on this data, and later on we use the trained model to make predictions on new data. Okay. So the machine learning can be, as we know, that can be unsupervised, can be supervised, can be used for clustering, classification, for annotating data. So all these topics are not new nowadays. It is the concept is being very old. However, we try to give a fundamental of this, to understand the fundamental of this, how the deep learning is related to machine learning, and how we can formulate or design a deep learning model for different applications. So to understand this, we know that the data is very much required. And if you talk about deep learning, the huge amount of data is required. So sometimes we call to distinguish it from the deep learning, call that machine learning is a shallow learning process. So where there are different shallow learning models, for example, support vector machine, linear and kernel regression, hidden Markov model, Gaussian mixes. So many models are there formulated in the as a part of machine learning, which has the limited modeling capacity, and we cannot also some of the time we cannot make the use of unlabeled data. Though there are unsupervised machine learning approaches are there, but it often happens. Now coming to the our topic now, deep learning. So as the definition says, it's a kind of representation learning in which there are multiple levels of feature. Now as we told that this deep learning is the base is the convolutional neural network. That means the concept of neural network is completely associated, and based on the knowledge of the neural network, we can formulate this deep learning. Means number of edge, we increase the number of layers in a neural network. We can say that this is a deep learning framework or network. However, they are not operated in the conventional artificial neural network. The operation is something different from that. So if we include multiple levels of multiple layers in a conventional neural network, where the features are developed or features are extracted from each layer separately, and they are being forwarded to the next and next layer. In this way, we can say that the features are automatically discovered, and final layer they are composed to produce the output. So in that sense, we say that each level represents abstract features that are discovered from the features present in the previous level, and the level of abstraction increases with each level. So if we increase more and more layer, what it says that the number of each layer produces some information, and the information is passed to the subsequent layers. Final layer they produce the output. So where if the number of layers increases in the form of DL, deep learning, so we can say that learning would be better. So if you see that compared to the conventional neural network, you can see that we have two or three layers. Where I have shown here a single layer for a simple neural network. Whereas in a deep learning neural network, we have multiple layers, maybe more than 10, 15, 50, hundreds of layers are there in a present deep learning neural networks. So mostly we use the framework or the concept of neural network, the how it is trained, how the connections are made, how the weights are trained, weights and biases are trained. So all these comes in the framework of neural network. So you can say that it's a kind of machine learning algorithm that uses multiple layers of nonlinear processing units. So the concept of nonlinear processing is same in the same as the simple neural networks that we have already studied in many years back. So those layers are responsible for extracting features and transform. So let us understand how. Then the question is like the natural question arises is though this neural network concept of neural network existed in many years ago, but we are not able to use those this in the form of deep learning extensively in the previous days. What was the problem? What was the issue? So this particular slide shows about the how the timeline flows. So here I have shown up to 2014. After that, also there are so many improvements made. We are in now 2024, where the deep learning frameworks, many deep learning frameworks have been developed and are being used for multiple applications. So the basic reason behind not to use this deep learning previously, because for as we know that deep learning requires a huge amount of data, and for processing a huge amount of data we require sufficient computing facility. Sufficient computing facility in the sense we have to use the GPU based implementation, for which we require a high-end computing system where GPU can be installed, graphics processing unit can be installed. So all these, though the architectures and concepts exist in previously, but we are not able to fully exploit the power of this deep learning. Rather, after 2012, with the successful use of GPU-based implementation, so complex tasks there, from that point we started using this and made the revolution. So one of them was on 2012 was AlexNet model that has won the ImageNet computation. So ImageNet computation is like classification of image. ImageNet is a data set which contains millions of images, and this particular network or deep learning model, we can say, will has been used to recognize those images. So by training with a very large set of data. So in that way, I can say that though we know the concept, architectures were present, but because of resource constraint, we are not able to use that. Now we are sufficient with these models as well as the resource computing facilities. So we are trying to exploit this deep learning for different applications. Now, this particular diagram shows that how though deep learning is considered to be a subset where we consider it as a subset? Because these machine learning involves with the data, as well as deep learning involves with the data training, classification. All these are performed in machine learning as well as deep learning. So learning takes place in both the scenario. However, the basic difference lies in the process, how it works. So in the machine learning, feature extraction is a separate step, where followed by the classification step, where I have shown that the shallow learning, the different models of ML models they exist. So which does the job of classification. So before that, we must know is a very crucial step in machine learning. In order to produce a good outcome, we must have to find out the feature which is very unique to a particular object. Now you can see that in the particular in this diagram, car input is the input image, where a feature extraction step is explicitly carried out before feeding it to the classification. So once features are extracted, which represent the uniqueness in the particular object, so based on that, a model can be created or can be designed to can be trained with the data, feature data, to produce the classification for car and not a car. Whereas if you see the deep learning scenario, we do not have worry about the do not have to worry about the feature extraction step, which is combined with the classification. That means, as I said, the features, because we increase the number of layers, and as the number of layers increase, the number of the abstractions information extracted from the particular input data is also being increased, so that we can say that features are not explicitly extracted by a domain by a separate step. Rather, the step is merged with the classification, and the features are automatically discovered from in each layer. Finally, they are combined. So which gives the name and as well as the framework as deep learning, where the learning is deeper and deeper as we increase the number of layers, which also does the same job of distinguishing or classifying the input object as car and not a car. So the basic difference, the important difference lies in extracting the feature, where extracting the feature is done in the machine learning by a domain expert, whereas in deep learning, it is directly done uh, in the neural network. Now, sometimes there are also mathematical proofs which shows that some function. So if you see the previous model, you can see the number of connections here. You can say that the huge, if you compare with respect to the conventional neural network, where because if number of layers are increased, so all neurons in each layer has to be connected, and there should be a full connection, so that as the number of layers increase, number of neurons increase, number of connections increase, number of training parameters increase. So somebody can think that if you try to form a deep neural network for a particular application, for targeting a particular application, the number of training parameters should be huge, and the complexity of the network increases, which can be solved by a very simple neural network. So, but sometimes what happens, there are also mathematical proofs which says that for some functions, shallow circuits also require more circuit elements than deep circuits. So we'll just try to understand this in the few slides later. So deep circuits can be intrinsically much more powerful than shallow circuit, because we try to extract much more information as compared to the shallow circuits, where we do not utilize any domain expertise, and there is no manual feature extraction step, where we try to extract all the features that are exist in the input data. Because this was initially targeted to for the applications like image recognition. So in image, we know there are so many features exist. If we are able to extract all those features by the network, so will be sufficient, will be having sufficient features which can recognize the agent. So in that way, this deep learning circuit has been framed, and we know that this can work better than the conventional machine learning and neural network models. Now, the basic idea behind this deep neural network is being developed using the concept of convolutional neural network, which is, as I told, the architecture, the concept exists. This is the person, the Licon and Bengio has in 1995 have introduced the concept of convolutional neural network, which is the base for the deep neural networks. Okay, so if I start with CNN, so they are also neurobiologically motivated by the findings of locally sensitive and orientation designed a network structure that implicitly extracts relevant. So what I mean to say, the concept of conventional neural network is same, almost same, the with respect to the training, with respect to the concept of finding the connection between different nodes. So all these remain same, only the difference lies in the operation. So we'll try to highlight that how they are different and how they are powerful than simple multi-layer neural network. It's also a feed-forward network that can extract topological property. Like all other neural network, they are also trained with the version of their propagation, as I told. The training of CNN and ANN doesn't vary much. They all, both use this wake propagation algorithm. But however, the connections that are made, which is very completely different, and there are different properties of conventional neural network with respect to their operation, with respect to their connection, which which makes this it different from the conventional neural network, and they are particularly designed to recognize pixel images minimal. I request all of you to mute if anybody. So, so I'll be open to any questions after I complete my presentation. So please listen to me carefully, because there are so many concepts that I'm going to discuss. So the concept of this is the architecture how of a CNN, conventional neural network, how it works. So you can see that there are few layers, different layers, named as convolution layer followed by pooling. So this convolution followed by activation with pooling are being repeated multiple times as per the requirement. Then once the features, this particular part is known as feature learning, where features are automatically learned and discovered. And finally, they are flattened and connected like a fully connected counterpart of same as your conventional neural network, followed by the final layer of softmax or any predicting layer, which can distinguish or classify the final targets. So example of network with many convolution layers. So if you try to frame many convolution layers to form a deep learning network, we can start with convolution, activation, pooling, and same thing is repeated. So in each layer, filters are applied to each training image at different resolutions. So output of each convolved image is used as the input to the next layer. So what happens? So we'll go step by step how these layers work, and what is the job of each layer, and how we get benefit out of each layer, why each layer is necessary, and how it is different from conventional neural network. So the layers can be the termed as like convolution layer, ReLU layer. ReLU is an activation layer that is same as your activation function as you use in neural networks, followed by pooling layer, followed by fully connected and softmax. So the main important part or important component of this CNN is the convolution layer and pooling layer. So let us try to understand how these two layers work, and what is this importance of two layers, and how it has been kept as a base for forming deep learning network. Now, if you go by the topology, we can say same thing has been shown in pictorial form. So feature extraction. So convolution layer can be also be written as feature extraction layer, and we have followed by subsampling layer or pooling layer known as shift and distortion invariance layer. So these two layers are repeated multiple times in order to create a final layer. Now with the to start with the convolution layer, so there are basically two concepts that are being used to make it very popular and to be useful for forming a deep learning network. So one of the concept is local receptive field, where it tries to get information from a local area or local region rather than from the global area. So what happens, like in conventional neural network, to form a network, we need to connect the neurons from one layer to the succeeding layer, and all there should be all connections, means a particular neuron in a hidden layer is connected to the all neurons of the previous layer. Okay, so if we do in that way, you connect all the neurons in the whole network, and you think, imagine if you have a 50 layer, 30 layer, 100 layer of neurons, if all the connections are made, so the number of connections will be exponentially large, and it is very difficult to train all these connections or the weights related to the connections. So what happens, instead of doing that, in the deep learning and CNN framework, what happens, instead of doing the full connection, we do a sparse connection in the by just exploiting the concept called local receptive field. So to understand that, we have taken here an example where, let us suppose, we try to recognize an image of size 28 cross 28, so which can be given input to any neural network with a neuron size of 28 cross 28. So this represents, each neuron represents one pixel, and in order to address, or in order to accommodate on this 28 cross 28 image, we require 28 cross 28 number of neurons in the input layer. So followed by another layer called hidden layer. Now you can see that, so the hidden layer neuron is connected to the input set with a local receptive field of 5 cross 5, and that particular neuron is not connected to any other neurons in the input layer. So this particular, the first neuron in the hidden layer, only responsible for connecting information from these 5 sets or 25 sets of input neurons. So this means it collects information from the 25 number of pixels. So it doesn't have get any other information from the whole region. So whereas if you compare that with other conventional neural network, all the neurons of first hidden layer should be connected to all the neurons of the input neuron. So that is not there. We won't connect every input pixel to every hidden neuron. Instead, we make only connections in small localized regions of the input image. So each neuron in the hidden layer will be connected to only. So this forms the local receptive field. This is termed as a local receptive field, which says that if that particular neuron is responsible for getting information from the local area rather than the whole region of the input image, so another neuron will be responsible for collecting information from a different region. So this is called local receptive field, and it's not always mandatory that we can connect only to 5 cross 5. We can also connect to 3 cross 3. We can also connect to 7 cross 7, depending on the requirement. So each connection learns a weight. Like if for this example, I have shown 25 number of connections to a particular neuron. That means we require 25 number of parameters to be trained along with the bias. If you add the bias, that becomes 26. So then what we do, we then slide the local receptive field across the entire input image. For each local receptive field, there is a different hidden neuron in the first layer. So like you can see here, for the for a new receptive field, we connect that to new neuron in the first hidden layer. So similarly, go on sliding the whole set from top left corner to bottom right corner. So in that way, we try to, each neuron tries to collect information from different regions. So in that way, we do not require full connections. So only you require a local receptive field or local information from the input data. So by doing that, we are drastically reducing the number of connections, which is which is very crucial, and which is related to the number of parameters that we want to train. Now, if so for this example, we have a 28 plus 28 input image, and we choose a size of 5 cross 5 for local receptive field. So if you do that, we require number of neurons to be in the hidden layer is 24 cross 24, because when you go on sliding the window from top left to right bottom corner, we can only reach up to the last button. So what it says that we move the local receptive field 23 neurons across and 23 neurons down before colliding with the input wave. So sometimes we can do the padding to increase the size of the region, and we can follow the whole 28 plus 28 to be the input. However, this is for this example only before colliding, only it can match with 23 neurons across and down. So that another parameter that comes into picture is the stride length, which says that how much distance we are moving the local receptive field for particular instance. Like we might move the local receptive field 2 pixels to the right, 2 pixels to down. So we can call that as stride length of 2. So in the previous picture, only we have moved, we can see that we have moved only 1 pixel towards right for connecting to the next neuron. That means we use a stride length of 2. So this defines how many pixels you are moving at a time to move the locally shifted field and to connect to a new neuron. So that is also a parameter. So based on the requirement, we can choose this what should be the our size of local receptive field and the size of the slide length. Then once we choose the local receptive field, how we can get that information? So the information is obtained by using filtering, and that process is carried out by using convolution operation. So convolution operation is a mathematical operation that is a very well-known operation in signal processing that we use for filtering any data. So in the similar way here also for CNN, we also use the same operation where we have a filter mask which is applied on a particular input data. You can see that the example is shown here. So in this example, we have 2 cross 2 mask size with filter coefficients and which is applied on a input data of 5 cross 5. Just a minute. Sir, I am having a presentation. After that, I will call. Sir, 1 hour. I will give it, sir. Okay. So, so this convolution layer is applied onto the whole input data and slided along as I have shown. So this is the same operation that we do in the convolution. You can see that this convolution operation nothing but multiplying each element, each data with the mask element wise and adding and summing them up. So you can see 1011 is applied on 1110, which gives a result of 2. In the similar way, this is moved across and down along the row and column to get information. So this is our local receptive field. So that the size of the local receptive field depends on the size of the filter mask. So this this is the mathematical definition for convolution. You can say FMGN minus N, very well known definition for convolution. So using this we can obtain information or filter out the information that is present in the input data. Same thing has been shown for image. You can see these are the images from the digit recognition database. So these images, because it's a black and white image, which are represented in the form of 1 and 0, and which is convoluted with a mask of 3 cross 3. That means we try to use 3 cross 3 local receptive field, and it can generate an image or generate an output as 4342, 43234. Just depending on the mask how we use. You can see that this mask is applied on the first top corner, then it is moved 1 pixels right after covering the whole length, and again we are moving down. So by doing this we are able to get information or feature map like this. So this operation is carried out once we fix the local receptive field. So this operation has given the name that network, neural network as convolutional neural network, where and this is about how if we have different filters, like in a particular layer, we try to generate extract features using a convolution mask, and we try to generate the feature maps. So for getting more information, we can use multiple feature maps or multiple masks to filter out the information that is present in the input. So if we have different filters of different size, HF, WF with channel C. So with this, they can be related like this. We'll obtain an output of H0 and W0 using this formula. Now you can see the feature map, how they are generated pictorially. So first one, the red one, which generates a mask, which generates a feature map. Another feature map also is being used to generate another feature map. So in that way, we carry out the convolution operation to generate different feature maps and different information required. So it's not always mandatory that two or one feature. There might be multiple feature maps generated as per the requirement. Now, same thing has been shown here. You can see that we require to detect the same feature at different positions in the input image. So, in order to detect the same feature at different positions, because this is required. So, what we can do, we can use the same mask throughout the image, and we can also use different feature maps to obtain different feature maps like this. You can see that a corresponding features are also shown. Now, another concept called shared weights and biases, which is also important concept, had led to the development of DL in an efficient way. So this concept says that Because we require same feature at all the positions. We can instead of changing the filter coefficients, what we can do, we can have the same weights or coefficients throughout the whole image. Rather than changing the filter coefficient, we can have another feature map having the same weights and biases, which is moved throughout the whole input data. So each hidden neuron has a bias and 5 cross. So here I have mentioned 5 cross 5 weights because we have, for this example, we have taken 5 cross 5. Is connected to local shift, and same weights and biases are used for each of these hidden neurons. So for each of these hidden neurons, this can be framed within a formula, a standard formula for getting the output of a neuron. So sigma denotes the activation, B denotes the bias, WLM, a, WLM is the weight associated with the filter mass. So 5 cross 5 varies from 0 to 4, and these neurons detect exactly the same feature. So if we use the same feature or same weights and biases for all the input data, that means we do not have to worry about the number of connections for a particular neuron, because the number of if we use different weights and biases and different filters for a particular neuron, what happens, for each neuron we have the number of parameters is drastically increasing, because it depends on 28 plus 28 into 5 or 25 plus 25. So that means the neurons which work for a to get a particular information will do not have shared weights and different weights, so which increases the number of parameters exponentially. So rather than doing that, because we try to keep the features same throughout the whole image, we can share the weights and biases throughout the whole image. So by doing that, we're drastically reducing the number of parameters to be trained. So we can see that for each parameter, for each neuron, we keep the weights and biases same. And like if you use three feature map, it generates a 3 into 24 plus 24 number of neurons. So three feature maps generates three images, three set of images or three feature maps, and where each feature map will give the same information from the whole image. So by doing that, if you compute the number of parameters, we have, I told that for local shift field of 5 plus 5 with a bias included, it gives 26 parameters. So if you have 20 feature maps, like I have shown three feature maps, if you have 20 feature maps like that, we'll get a number of parameters to be 520. In comparison, fully connected, if you say that we do not have to worry about the shared weights and biases and we require a full connection, so the number of connections we use at least 40 times as many number of parameters. So this concept of shared weight and biases has resulted in faster training for the convolutional neural network. Ultimately, this helps us to build deep neural networks. So this is about what are the different activation functions. This is same as we already know in the commonly used activation functions in neural network. So basically, in the convolutional neural network, ReLU activation functions are used. Most of the cases we use ReLU activations. It's not mandatory, but also we can use other. So most of the cases we use ReLU activations. So it is being used for learning. So we use that. We use that activation feature map to learn the function. So this shows that how ReLU is acting, and its comparison with sigmoid. Sigmoid is also a very popular activation function. Most of the cases we use, and if you compare that, you can see that ReLU activation function is better than the sigmoid. If you see our convergence, and this is the with activation function, you can see that the training error reduces very fast with respect to ReLU as compared to 10H. And if we provide a value to this value matrix like direction, it suppresses the negative values and makes it 0. Now this is the picture representation for how these input feature, once they are convoluted and we get a feature map. So they are provided to the rectified feature map or generated a rectified feature map using value activation function. So negative values are suppressed. Now, once they are rectified, this feature map, we use the pooling layers in the CNN. So this pooling layer are usually used immediately after convolution layer. So what it does, it simplifies the information in the output from the convolution layer. So why simplification is needed? So one of the reason could be like suppose we have a bigger matrix. So that instead of just processing the bigger matrix in the next layer, what we can do? So one of the possibility could we can summarize the whole matrix in very few elements, and so that is called pooling. So summarizing or suppressing the information or reducing the number of information. So pooling layer takes feature map from convolution layer and prepares a condensed feature map. So each unit may summarize a region like in the previous. So instead of summarizing the whole matrix, we keep a region for a small region for pooling operation, and we represent a particular element out of this whole region. So one common procedure is max pooling. Max pooling in the sense it is like we choose the maximum of all elements. So you can see 24 plus 24 neurons from convolution layer. After pooling, we will have 12 plus 12 layer. So you can, that means you are going to reduce the dimension by half. So why we do that? Because most of the cases, once we use multiple feature maps, there might so happen that the number of the information that is present in the output of the hidden neurons will be almost similar. So instead of providing the whole information, we try to concise those and use a subsampling method to reduce the data. So this, in that way, we can summarize the information as well as trying to reduce the number of parameters to be provided to the next layer. So these are different pooling methods: max pooling, average pooling, stochastic pooling, commonly used in CNN. So advantages, as I told, advantages are they reduces the computation burden because we are subsampling and reducing the number of samples to be processed for the next layer. So obviously it reduces the number of the computations required for the subsequent layers. And another advantage, important advantage, lies in the active pool map is they are less sensitive to the precise location of the structures. So what happens wherever the structures are located, so that doesn't have any effect on the pooled map. That means if a particular feature is present in any of the positions, so they are very sensitive with respect to the locations. Okay, so we are able to capture that information with the help of pooling. Another thing is we make the representation invariant to the slide translation. So some of the cases, what happens, because of different environmental issues or environmental conditions, there are different translations in the input. If the translations affect our feature extraction process, so that is a very challenging to address that particular point. Though whatever model we create, that must have to be invariant with respect to the translations in the input. So this pooling methodology or pooling technique helps in doing that. So it poses like our model is invariant to the CNN model is invariant to the translation. So because of this, all these advantages, pooling are being used in CNN. So one of the example is also shown here. You can see that activation, average pooling of data, max pooling, maximum of all the data. Then we create a probability map or probability stochastic pooling. Once we create a probability map, then the corresponding high probability element is being extracted. So we can see that the different pooling techniques generate different results. So based on the requirement, we may go for any pooling technique. Now you can see. So first we do the take the input with a 28, let us suppose 28 cross 28, and with a convolution mask of 5 cross 5, we obtain an output for 3 feature maps as 3 into 24 cross 24. So once they are pulled with a suppose any max pooling technique, we are going to reduce the number of elements by half, by 3 into 12 into 12. So in that way, so this particular process is repeated multiple times in a deep learning framework. So once they are repeated multiple times, so finally we come to the fully connected layer, which is the same as your conventional neural network. So I'll not go deeply into that, because this layer are being used in any conventional neural network. So what it does, there is a fully connected layer, means all neurons are connected, like conventional neural network. But previous cases for convolution and pooling layer, connections are not full. So followed by complex layer or probability layer for to generate the predicted score or the classification. So putting all together with the whole network, so we can see that the connected layer with they are flattened all the neurons. So these neurons represent the number of classes to be used. So this deep convolutional network, we use special architecture, advantage of special structure, particularly well adapted to classify images, because they are targeted for images information. So this term has trained deep many layer networks very good at classifying. So the concept of shared weights, local receptive field, and pooling has generated the birth of these deep learning frameworks, which is very easy to train, and though it requires many data for better training, but if you see the feature extraction is done automatically. So there are many advantages of deep learning framework using the concept of CNN. So they are being primarily used for many such applications like image recognition. Though there are advantages, there are some disadvantages as well. You can see that from memory and standpoint of view, it is not much efficient, and runtime convolution operations are computationally expensive, and they might be slower than the fully connected equivalent. Like if you compare CNN or deep learning application with 100 layers with a 3-layer MLP, so you will definitely see that the number of connections with respect to, though we are doing sparse connection or using the concept of local restricted field, but number of parameters will be huge in the deep learning framework. So in that context, we can say that the complexity is somewhat higher. But there are some applications where we require to create a deep learning layer, a deep learning network with large layers. Okay, so which cannot be solved using a very few layers of neural. The solution I already we are using the railway activation is very faster to make it fast with railway activation functions. And if you having a facility of GPU, so obviously that I told that to train a deep learning network, we require a high computing facility, including GPU, having larger memory capacity, having parallel computing facility. So all these things are required in order to fruitfully use the deep learning for different applications. So another idea is the transfer learning. So it's very important, and most of the cases we try to use this concept to train our network. So this transfer learning concept is the concept of inductive learning, which is the learning framework or learning concept we studied, we know in the machine learning. So from one knowledge another knowledge, or one knowledge is used to solve another problem. That means storing knowledge gained while solving one problem, so applying it to a different but related problem. So for example, suppose we trained a model can be used to recognize drugs. So if we have a similar problem, like we know that there are so many problems which are similar. And suppose I have designed a network, a bigger network, and to recognize cars. So can I use the same network to recognize trucks? There are lots of similarity. So if network is capable of recognizing one type of vehicle, the same network would also be used for detecting or recognizing another type of vehicle. to transfer line. What it does, so we try to load a pre-trained network, and each layer you can see the first set of layers obviously try to extract the low level features that are edges, blobs and colors, and last layer that and last layers that trains. So this is what we can take the weights as it is already been derived by the by training with the bigger size of data. So we can keep those weights fixed, and we can start from that point to learn a new task. It is very fast, and with a smaller number of training images we can do that. And we have seen that it is also observed that number of parameters for the new network would be very small as compared to the bigger network. So this is the example LXNet I told initially. This is the network where you can see the number of layers. The same layer is being repeated. Max pooling, convolution layer with different mask sizes are being there with. So finally, it is ended up with a fully connected layer and deriving the 1000 class or recognizing the 1000 class problem. All other well-known networks shown in up to 2015. There are many more such networks have been developed with different number of parameters. Now coming to the after completing the CNN concept of, very briefly I have described the concept of CNN, which is very popular for forming a deep learning model. So we can see that CNN was primarily targeted for image related data. That means we can target or we can classify or recognize or can extract features from a two-dimensional data. Now think of a scenario where the data is dependent, the current data is dependent on previous data. That means if you compare that with a movie, suppose somebody wants to explain a movie from a particular point, so we need to know. So we cannot do that job because you don't have an idea what has happened before the starting point. So you must know what has already been there. Based on that, means they are related. The outcome of this particular event is related to previous data. So we cannot throw everything away and start thinking from the scratch. What we can do, so we can we can memorize from the previous information, and from the previous information we can generate a new information. So traditional neural network is not able to do that. So this is a very major shortcoming of the CNNs. So what we can do, we imagine you want to classify a kind of event is happening at every point in a movie. So it is unclear how traditional neural network could use its reasoning about its previous events in the film to inform later one. That means we need to know what has happened previously based on because these past events are related to the present event and present. So all these events are used to calculate the next event. So in that sense, the CNNs are not so helpful. That's why this recurrent concept of recurrent neural network has come out. So this is also the training. All these things is same as your neural network. However, the way the connections are made is a little different. Now you can see that. And so this is called temporal dependency. That means the data are dependent on a time basis. That means temporal dependency. So this temporal dependency is mostly used for analyzing video data, where video data is framed out like a frames, continuous frames targeted at different times t. So we can see that this RNN is structured like this. A is a network node. You can say there's a neuron in the neural network, which is recurrent in nature. That means there is a feedback connection from the output to input again. So it can be thought of as a multiple copies of the same. So if you try, so this is a simple node structure in RNN. So to form a RNN, we have similar structures connected back to back. Okay. So if you try to open up this, you can see like this. The x0, x1, x2, xt represents the input data, and the output of a particular node, like let us suppose here h1, depends on the output from the previous node as well as the present input. That means there is a dependency, means what output it generates. This particular output h1 depends on the outputs of the previous node. That's, you can see that can be framed mathematically like h of t is 10s. So 10s is the activation function treated here, and WHS HT minus 1, WHX XT. So XT represents the present input with associated with WHX, and WHS is the associated with the previous output HT minus. So that means the dependency of HT with HT minus 1, H, HT plus 1 with HT, and so on. So this dependency can be handled very easily using this RNN, which is very much suitable for analyzing the time series data. Same thing in the form of a symbolic representation or graphical representation has been shown. We do concatenation from the previous output HT minus 1 and present input XT in order to generate a new output HT. Several nodes connected together back to back looks like this. Now there is this is all called, you can call that as a vanilla RNN, where number of nodes are connected and we try to create the output or get the output from the previous and present input. But though this is capable of learning the dependency in the data, but not capable of learning long-term dependency. So because of the gradient vanishing factor. So what we do during training of any neural network, we use gradient for in the back propagation. So the gradient factor or gradient magnitude must be significant enough to train the network. However, what happens if there are long-term dependency? If you use a large set of layers for in the form of a deep learning, what happens? The gradient decreases significantly while it coming back to the input layer. That means some of the layers are not being trained properly. So because of this problem, that RNNs are not suitable, mostly suitable for handle long-term dependency. Long-term dependency. So further development to this RNN is a long short-term memory, so which tries to solve some of the problems of long-term dependency. Though it is not able to solve fully, however, somewhat better than RNN. So why? Because it is having two major characteristics. One is information persistence, another one is prioritizing information. So information persistence is done using that. That means it keeps the memory whatever happened in the last moments or last event, what has happened. So that is done using cell state. Cell is nothing but as a memory element. So like they are conveyor belts that runs across the time to which the information are being carried out in a conveyor belt which are memorized. Okay, that is one important characteristic. Another important characteristic is prioritizing information. So all the information that is coming from the past are not so useful. So what it happens, what it does, it tries to filter out the information those are not useful for future, and they are thrown away and erased, and it passes only the information which are useful. So this is like a gate, the information are flown through a gate. The gate selects some of the information and pass to the next layer and discards other information. So this is the structure. You can see that it has multiple operations, unlike RNN. So RNN only takes the feedback from the output of the last node and tries to get the output. However, in the LSTM, uses different gates to filter out the information from the input data as well as from the past data. So using these four modules: cell state, forget gate, input gate, and output gate. So using these gates, it tries to filter out. So let us see one by one. Cell state is the information to memorize. It's like a horizontal line or conveyor belt. It runs straight down the entire chain, so with only linear interactions. So it only keeps the is responsible of keeping the information and to be flown through the next state. Forget gate is responsible for filtering out the information which is not useful and only transmits the useful information using a gate. So that gate means we use some person. So mathematically we can write that as using activation function, sigmoid activation function, which works on the input data and only filters out the information that is required to be flown to the next state. Input gate. Input gate tries to filter out the information from the input data, which new information is important. Now cell state is updated with the input data and the previous output. Then output gate decide which are going to the output, and it will based on the cell state what is the filtered version. So all this LSTM works in on a filtering basis. There is the different filters are being or window functions are being used to create information that is required to be flown to the output using different filters. Now, once we understand the concept of CNN, RNN, LSTM. We have understood that CNNs are responsible for and can produce very good result for a spatial data like image, and RNNs and LSTMs are suitable for handling the temporal dependency because they can memorize the things and generate the output based on the past output and present input. So those RNN, LSTM, and CNN can be used for analyzing time series data, video data, all these things. So here we try to focus on a particular computer vision application for video analysis and finding anomalies. So to start with, let us understand, because this is very fundamental and all of you must I hope that you know that what is a video, all these things. I'll not focus much on that. So to represent a video, you require spatial coordinates XY with a temporal coordinate T, and frames are being repeated at a particular frame rate to make it as a video, which are nothing but sequence of images. So the main challenge here is to how to model T, because we know that how to model XY, how to model T individually, but we in the video analysis we require to both model XY, spatial coordinate, and spatial information as well as temporal coordinate. So there are some of the methods that were being used for analyzing video for different applications. So these are the different applications. You can see that how robotic manipulation can be done using video, self-driving cars, collective activity understanding the different activities in a video. So all these tasks are being usually carried out using this CNN, RNN, LSTM networks, classifying a video. So if you see what is the it's a difference video classification, because this is the video classification task. What I'm going to describe is a video classification task. And if you see what is its difference with respect to image classification only requires spatial data. Our video classification spatial along with the temporal data. So the challenge lies in analyzing the both at a time in order to create a video classification model. Now, before deep learning has started, there are also some of the machine learning techniques were used to classify the video or analyze the video using features like local features like histogram of gradient, histogram of optical flow, trajectory-based features. We were trying to aggregate those features using different techniques like bag of visual words, bag of feature vectors. So all these were being used before deep learning has been introduced. So video classification technique through the time time axis can be classified like this or can be termed like this. Initially we started with frame level aggregation, then followed by two stream 2D CNN, followed by recurrent network, followed by 3D convolutional network. So they are all their advantages and disadvantages. You can see that frame level aggregation, temporal information is lost. Here you can see that frame level aggregation. What we do, we try to represent the video in terms of different images at times t, I want to it. Then we can use this conventional CLN like VGG inception model to create the frame level features. Finally they can be aggregated. So though we are able to extract information from the spatial images, but we are not able to model the time fully. How the exons are defined, how, because this exon, the exons classification is mostly concerned on deriving the images or deriving the spatial information with respect to time. So this is a network that can be used to extract frame level feature. It's the same as your what we have understood, convolution, ReLU, fully connected, all these things. Now, regarding aggregation or fusing the different frame level features, we can use single frame feature. We can use, so single frame feature will not work for any kind of video analysis. We can have different fusions like late fusion, early fusion, slow fusion. So to see how this frame level aggregation works for modeling the time dependency. So this is another case where multi-resolution CNNs for frame level aggregation can be used. So we can have two different streams. So one is targeting the higher resolution like phobia. Another is targeting another sequence is targeting for analyzing low resolution. So because video contains different frames having high and low resolution, so people have thought if you use two streams TNN, two streams CNN, one for targeting high resolution, one for targeting low resolution. So these are the basic ways how these things can be solved for managing the time. The summary says that The frame level pooling mechanisms provide video descriptor which focuses on the salient instances, and the video descriptors for each videos are treated as data samples for classifiers. Like once we get the features from different streams of 2D CNNs using 2D CNNs, finally they can be classified using conventional machine learning classifiers. But though they are able to generate some feature, but they are not capable of modeling the temporal information. Only they are able to get the frame level features. So the natural question still remains how to model the temporal information. So the temporal information, as I told, that can be done by just extracting the information from the time, how the actions are moved from one frame to different frames. So one of the procedure was optical flow. So optical flow is same as getting optical flow as well as spatial information can be considered as a 3D CNN architecture when one stream is dedicatedly targeted for getting the optical flow. But though optical flow we are able to detect from the different frames, but they are not aligned with the image spatial information. If spatial information and temporal information are not aligned properly, it is very difficult to recognize or finding the video class or finding any objects or finding anomaly in the that may be present in the video. So you can see that spatial stream and the temporal stream, they were trying to analyze with optical flow and spatial information. They are fusing the class core. However, they are not they are not able to get the proper information aligned with respect to spatial and temporal, lacking the modal temporal evaluation, not aligned. So we have done a case study for activity detection, abnormal activity detection in an untrimmed surveillance video. So these are the we have experimented on a particular data. You can see this is a data set obtained from crime data set, which is also already available in the literature. So it shows some of the frames which are abnormal or some anomaly events are happening, and some of the normal frames. So using this, we tried our experiment and we created a network to model to identify the what are the different anomalies present in a untrimmed video in the sense we take a long 2 hour 3 hour video. In that video we try to extract the frame level features and extract the temporal information combined together with the different pooling mechanisms and try to identify or detect the anomaly and what happens, what is the kind of anomaly and when it happens. So both are being done. Those can be termed as detection versus classification. So in the detection, we only detect what whether anomaly has happened or not in a particular time at a particular time. And once we detect the anomaly, that further can be derived what kind of anomaly, because there are some scenarios where it seems to be abnormal, but those abnormal cases may not be serious enough to be taken further. So there are some events which are very serious enough, which has to be attempted very urgently. So in that case, we need to classify the event as well. So this particular task, what we have in the case study, we try to detect as well as to derive the class of anomaly as well. So in this particular task, there are multiple challenges involved. So these are the challenges that are being attempted for addressing these challenges in many of the research papers. You can verify this particular topic for how these challenges are addressed by using different networks. So here we try to address these challenges, some of the challenges like sparsity of anomaly. So to discuss with the challenges, we start with unavailability of large annotated data. What it means, like we take a long hours of video which are not available with annotation. Like some videos contains like in a 2 hour video, some videos contain anomaly, some videos doesn't contain anomaly. See, this annotation is very important because whatever networks we have just discussed, those networks are supervised networks, so they require a level data. So in this particular task, there are not much level data available. So this is a serious challenge. Another one is the sparsity of anomaly, but what it says that in a very long untrimmed video, that anomaly may happen for a very small amount of time. So that shows the sparse nature of the particular event. within the complete video. So those can be handled using loss functions, longer duration as well. Longer duration of video data is very difficult to be analyzed. So we can somehow use to tackle with that address. And there are also common challenges like occlusion, illumination, low camera framing, short and long anomaly activity. So all these can be addressed one by one, or you can see these are the difficult challenges which come with this class. You can see the occlusion where the anomaly can be obstructed by different objects. Illumination variance. So you can see that three different frames have three different illuminating conditions. So identifying a particular or detecting a particular event in different conditions is very crucial. And at different time, what happens when it happens is very critical. So this is a framework what we have utilized and modified this framework to a little bit so that we can try to identify the anomalies. So what it does, it takes a two sets. One contains the anomaly bag and one contains the normal bag. So from both the bags, we try to extract features. So this model has already been proposed. We try to modify this model with a loss function and other networks for feature extraction. So here, multiple instance ranking loss function is used to differentiate the score, because you can see that anomaly and normal segment has a score and which is very different from normal score. So we try to maximize the margin of separation between anomaly score and normal score with a loss function. So this is the loss function that has been used in that particular framework, so containing temporal smoothing and sparsity constraint. And this, once we are able to detect the anomaly, then we can classify using the same classification model with a cross entropy loss. This cross entropy loss is a commonly used loss function for classifications problem. So once we are ready with the problem, we can use the same for identifying the anomaly as well. So you can see this is our network, or we propose one of our research group proposed this particular network, which tries to extract the framework remains same with some modifications like pooling techniques and LSTMs have been used for, and loss function. There is a modification in the loss function as well. So we try to extract features, special features using I3D network. So this is a three-dimensional CNN network followed by LSTM followed by pooling operations along the intra frames and inter frames. So by doing that, we are able to capture the subtle information from the video data to identify the anomalies with a ranking loss function. So these are the experimental details. 64 frames clips has been taken. Mean max pooling and max pooling is being used. UCF crime dataset is used. And these are the observations. So this is a this work is carried out in 2020, around 4 years ago. So further development also have been made to this, and performance improvement also have been carried out. This is the, and regarding qualitative analysis, you can see that this red one says our prediction and green shows the ground truth. So for a particular activity, shoplifting activities, which is in the data set, you can see that green is matching with red. However, this red says that this anomaly has happened before the actual anomaly is there, but we are trying to identify just the time of the anomaly, what has happened, and also able to classify the event. This is another event for which ground truth and prediction scores are shown. You can see that the red is matching with green. However, there some is extended towards the more number of. This means that the current model says that the anomaly has happened for a longer duration of time, existing till 1,000 frames. However, this actual happening has stopped around 300 frames. So this is the difference of prediction. So has been improved nowadays by using different modifications. This is another case where ground truth and predictions have been plotted for a different scenario. So these are the references used for this task. Thank you all. This is there. I am stopping and I'm able to questions here because I tried to concise all CNN, RNN, LSTM followed by a problem very quickly. I know that this is not possible to understand everything in a very shorter period of time. We require, because each of these topics and for mathematical understanding of each of these topic, we require multiple classes. Okay, so still I hope that you have understood something. Any questions if you have, I'll be happy to answer. Thank you. Any questions? I think there is some issue with by my. Please, I think there is some issue. I'm not able to hear from anyone. So you can put your questions in the chat. I can answer.
Professor Ratnakar, am I audible?
Yes, yes, I'm able to hear.
Sir, Professor Ratnakar, am I audible? Hello, sir.
Yeah.
Yes, sir. Sir, thank you so much, sir.
Yes,
for
you are audible.
Yes, sir. Yes, sir. So many. What happened, sir? Introduction section.
Am I audible?
Yes, sir. Yes, sir. You are absolutely audible, sir. Sir, introduction section. There was some.
Am I audible or not?
Yes, yes, sir. You are audible, sir.
You please.
Yes. So some technical glitch was there. So my voice was introduction section. People have not listened properly. So for the participants, I want to introduce Dr. Ratnakar Das. He is associate professor in the Department of Computer Science, NIT Rourkela, and he is also head of the Unit Center for Technology Enhanced Learning in the Department of Computer Science, and he has published more than 80 publications and successfully completed 2 sponsored projects, and 19 doctoral students are under him. He heads the Intelligence Computing and Computer Vision Research Group, focusing on the cutting edge areas such as computer vision, machine learning, and deep learning. Dr. Das is also deeply involved in continuing education initiatives, fostering advanced learning and research in artificial intelligence and related fields. His expertise and dedication have significantly impacted both academia and industry oriented projects. So, this is the short description for Professor Ratnakar Das. I am the BTech student when Ratnakar sir was in Roland Institute of Technology, Barampur. I was a student, BTech student there. Sir, my name is Vishnu Prasad Misra, sir.
Okay.
Sir, 2009 pass out students.
Okay.
Sir, you can see my camera, sir. So, yeah, thank you, Professor Ratnakar sir. And if there is no question, so we would like to end the session now. And I'd like to Dr. Bamsi Krishna, please provide the felicited Dr. Ratnakar sir with digital memento. Please accept, sir. Bamsi sir, please. Bamsi sir, please. यहाँ से हुआ है
Yes.
यहाँ पे शेयर शेयर बटन दीजिए यहाँ से शेयर बटन दीजिए नहीं नहीं यहाँ से नहीं तो हमसे सर शेयर करें हो रहा है
Here it is visible. Here it is coming. Here some problem is there. It's coming.
It's coming,
It's
sir.
coming.
No problem. Okay, okay, sir. Coming, sir. Question, sir.
Thank you once again, Professor Ratnakar, sir.
Thank you, sir.
You have given valuable time, sir. Thank you for all. I hope this session finds well for all the participants. They can utilize this session. We'll ask, request the Ratnakar sir to share the PPT to us so that we can share our participants if they're needed.
Okay.
So after the end of this session, we'll circulate some 5 to 6 questions, objective questions. So
Yes.
for the attendants, they have to answer this.
Okay.
And okay, thank you all
Thank
for
you.
your cooperation. Thank you. Thank you. We'll end the session now. Okay. Thank you.